Hello everyone, today we're talking about linear independence. This is material from 1.7. Let me, to motivate this, let me recall an equation, or I guess system, of the form ax equals 0 is called homogeneous. We talked about this last time, so the idea here is I'm writing this in terms of the matrix equation. A is some m by n matrix, and I want, x is my unknown, and I set this equal to 0. The right-hand side is 0, if you like. That's called the homogeneous system, and this always has a solution, the trivial solution, if I take everything just to be 0. So if I take all values of the variables to be 0, that's always a solution because it always works in each equation, right? And so today we're going to kind of translate this to, or investigate the underlying vector equation of a homogeneous system. And let me do this with an example. So for example, if you had, and let's do a little 3x3 system here. If you had this as the matrix A times x equals 0, right? So this is the same thing, it has corresponding, this is supposed to be an R, you know what I mean, vector equation. So what do you do? Remember, x is a variable, x is a vector. Its entries will become the weights of this linear combination. So this will be x1 times 1, 2, 3, plus x2 times 4, 5, 6, plus x3 times 2, 1, 0. And this should equal 0, 0, 0, right? That's the right-hand side of this equation. And, as we said before, this system always has the solution where you take x to be 0. And notice here, of course, it has the same story, that if I take x1 to be 0, x2 to be 0, x3 to be 0, it also works. So this, again, has the trivial solution. X equals 0, 0, 0, where I've taken every value of those weights to be 0. So that's going to be kind of inspiring our following definition. So a set of vectors, we call them V1 through Vp, let's say I have P of them. Let's say that these sit in Rn, meaning that they each have n entries. This will set to be linearly independent, so that's our main definition of the day here. Linearly independent if the underlying vector equation, where I take, x1 v1 plus x2 v2 plus, let's say xp vp is my last vector, set that equal to 0 if this vector equation has only the trivial solution. And of course, what that means is x1 equals x2, they're all equal to 0. Okay? So we know that that's always a solution to this vector equation. If it's the only one, we call it linearly independent. And, well, if you're not linearly independent, that has a name as well. You might have guessed this. Let me see if I can keep both on the same page here. So if a non-trivial solution exists, to that vector equation, so what does that look like? This is going to be c1 v1 plus c2 v2, let's see, cp vp. And so what we need now is that where not all of the ci's equal 0, then we say the collection is dependent. So if you can write, I should have said this equals 0, right? So a non-trivial solution will be some choice of weights where you make a linear combination and it equals 0, and yet not all of those weights are all 0. Some of them could be 0, but at least one of them has to be 5 or -2 or something. So we say in that case that it's linearly dependent, right? And this thing here has a name. This is called the linear dependence. So that will be an actual solution to a non-trivial solution to that vector equation. Okay, so let's do this with a little example here. I think, once again, this is a concept that has a new name, but it really boils down to something we've been studying, so far this semester. Just yet another perspective on systems, basically. So let me give you a V1 is 1, 1, 2, 3. V2 is 4, 5, 6, and V3 is 2, 1, 0. And I want to know, is the collection V1, V2, V3 linearly independent or dependent? Yeah. So how do you solve this? Well, right, we're going to look at the underlying vector equation, and right, which we can immediately translate to a system. So to answer this, we're going to consider the system. Right, again, we're really looking at a vector equation, so this should look familiar. This is the same vector equation that I introduced things with. So we're going to look at the system corresponding to the relevant vector equation. I'm going to kind of skip that step and just write down the system. In other words, it's going to be what? What do I do is I take 1, 2, 3, 4, 5, 6, 2, 1, 0. Those will be my, that's my coefficient matrix that I get by taking the vectors. And I want to know, can I write these, to make, in a linear combination, to make the vector 0, 0, 0. So you're always augmenting with 0, 0, 0 in this context. And I'm going to skip, the row operations. I press my magic row operations button, and I get 1, 4, 2, 0, minus 3, minus 3, 0, 0, 0. Now I know the right-hand side is going to be 0, 0, 0 because we've talked about this before. When I have a homogeneous system, I row reduce. This is now echelon form. I'll always have the 0, 0, 0. Okay, so what can I conclude from this? I've got pivots here and here, right? So what this is saying is that, right, we know that this is a consistent system. It'll always be consistent. But what we're seeing is that x3 is free. x3 is a free variable, which means that this implies that the system has, well, non-trivial solutions. In fact, infinitely many. We know there's infinitely many solutions. And so what the punchline of that is, that says that, this implies, remember the definition of linear independence means that the system has only the trivial. So this means that the collection is not linearly independent, so it's linearly dependent because we had non-trivial solutions to the corresponding system there. And maybe just to kind of riff on this example a bit more, what if I now asked you, can you actually find a linear dependence? Well, again, something that, sort of new words for something we already know. This is just asking for a particular non-trivial solution for this system. So let me go through and actually, do that for you. So for this, we want the solution set, right? We want a description of the solution set. So as you know, right, what you do is you further reduce row echelon. If you do that, what you get is 1, 0, minus 2, 0, 1, 1, 0, 0, 0. Of course, there's zeros here. And what is this telling me is that the solutions set is given by, in vector form, it's going to have 3 variables. And if you work it out, what you get is x3 times 2 minus 1, 1. If you haven't done this too much, I recommend going through that calculation. But okay, so all solutions will look like this. So now we can actually, as usual, this is a free variable. x3 is free, so we can now pick our value of x3 if we want an actual solution. So let's take, I don't know, x3 to be 1, I think is, now we don't want 0 because that would give us the trivial solution. And what do we get? We get 2 minus 1, 1 as a solution. And let's see if that works. So what I'm claiming is if you go back right, to those vectors there, let's check it out. What happens when you take 2, right, that's my first guy, 2 times the first vector, plus minus 1 times the second vector is 4, 5, 6. That's the second weight, plus 1 times the third vector, which is 2, 1, 0. Let's check it out. So what do you get when you take this linear combination? This is 2 minus 4 plus 2 is 0. 4 minus 5 plus 1 is 0. 6 minus 6 plus 0 is 0. So it works out. That is a dependence, among these vectors, because it's a non-trivial way to write those vectors in a linear combination to get the 0 vector. Okay, so I think just to summarize now, maybe just to summarize kind of the fact that we've been using, but just to have it kind of written down, is that the columns of a, let's say, m by n matrix A are linearly independent, if and only if the equation ax equals 0 has only the trivial solution, x equals 0. Okay. Let's see, maybe I'll just do one quick example here. So what if A is, just to throw one more example at you here, 0, 1, 4, 1, 2, minus 1, 5, 8, 0. This is a matrix of 3 by 3. It reduces to the following row echelon. So it goes to 1, minus 1, 1, 2, minus 1, 0, 1, 4, 0, 0, 13. Now notice that I did not augment this thing with 0, 0, 0 because, as I said, I don't care, right? I know it's going to be always 0, 0, 0 on the right-hand side. So, as I said, it's typical in this case to, you can think about having a secret column of zeros there, but you actually don't need it. What do I see here is I got pivots in every column. So what that tells me is that there's only one, there's no free variable, so there's one and only one solution to this homogeneous system. This implies that the columns of A are indeed, let's say, linearly independent. Okay, so that's the basic idea with these notions. We'll pick this up next time. I'll see you then.